student, now we will deal with our chapter 3, electrochemistry. This is the electronic concept of oxidation and reduction, and electrochemistry is the study of the production of electricity from energy released during the spontaneous chemical reaction and the use of that electrical energy to bring about non-spontaneous chemical transformation. So getting the electricity from any chemical reaction is known as electrochemistry, and the redox reactions takes place during a chemical reactions. So what is a redox reaction? Redox reaction involves the oxidation and reduction of the species. The oxidation is a process in which an atom or ion loses one or more electron. So oxidation can be remembered as OIL. Oxidation is loss of electron, and reduction can be remembered like RIG. Reduction is gain of electron. So oxidation is a process of loss of one or more electron, or we can say there is an increase in the positive valency and decrease in the negative valency. Whereas reduction is the process in which an atom or an ion gain one or more electron. So there is a decrease in positive valency and increase in negative valency. Oxidation and reduction must occur together. So they occur simultaneously. Without oxidation, no reduction will take place, and without reduction, no oxidation can take place. So in this way, a galvanic cell is formed in which a zinc rod is dipped in a zinc sulfate solution and a copper rod is dipped in a copper sulfate solution. They are connected externally by a wire with a voltmeter, and internally they are connected with a salt bridge. So in a zinc act as an anode in a zinc container, Zn is converting into Zn2 positive. There is a loss of 2 electron, so zinc is undergoing oxidation, and where the oxidation takes place, the electrode is known as anode, and the copper is gaining the 2 electron and get converting into Cu, copper metal. Therefore, there is a gain of electron take place, and the electrodes where the gain of electrons take place or the reduction occur is known as cathode. So always remember that anode is the oxidation electrode and cathode is your reduction electrode. Anode is our negative pole, whereas cathode is positive pole in our galvanic cell or the electrochemical cell. So in a chemical cell, we have studied that Cu2 positive gaining the 2 electron changes into Cu, and this is our reduction half, and Zn is changing into Zn2 positive plus 2 electron. Loss of 2 electron are there, therefore this is our oxidation half. The oxidation half is our anode part and the reduction half is my cathode part, and the cell reaction can be written as Zn plus Cu 2 positive give rise to Zn2 positive plus Cu. This is our cell reaction. Now what is a cell potential? The EMF of the cell is positive and is given by the potential of the half cell of the right hand side minus the potential of the half cell of the left hand side. So we can say E cell, electromotive force of a cell is electrode potential of anode minus electrode potential of cathode. So E naught cell is your E cathode minus E anode. To represent a cell, the anode is kept on the left and the cathode is on the right. In anode, metal is represented first followed by the metal ion. In cathode, metal ion is represented first followed by the metal. But put a vertical lines between the metal and the metal ion. Put a double vertical line which represent the salt bridge between the two electrode. So in this way we can represent the two cells. Cu oblique Cu2 positive, then two lines are there, vertical lines, and it is your Ag positive oblique Ag. So here one is your right side, right electrode, and the next one is your left electrode. So E naught cell is always your E naught cathode minus E naught anode. E naught is for the reaction as return, and the more positive electrode E naught value, the greater the tendency of the substance to get reduced. The sign of E naught changes when the reaction is reversed. Changing the stoichiometric coefficient of a half cell reaction does not change the value of E naught. So whenever these E naught values are arranged in increasing order of their reducing strength, they form a series, and this series is known as electrochemical series. In this series, the value of E naught, which is below, which is down, is your oxidation, and the one which is upward is your reduction. So again, oxidation will act as an anode and reduction is going to act as an cathode. So a redox reaction is feasible if the electron releasing species is present at the position lower in the series as compared to the electron accepting species. So to find the relative strength of the oxidizing and reducing agent, we use this electrochemical series. Lower the position in the series, higher is the tendency to get oxidized and act as a better reducing agent. More negative the reduction potential, stronger is the reducing agent, and vice versa. More positive the electron reduction potential, stronger is the oxidizing agent. And for the help of calculating the EMF of the cell, here E naught cell is equal to E naught cathode minus E naught anode. We also find the feasibility of the cell by using this series. If delta E cell comes positive, this means the cell reaction is feasible. If it comes negative, it means it is non-feasible. And if it is 0, it means it is equilibrium. To predict whether metal can liberate hydrogen ion from acid or not, more negative the value of reduction potential with respect to hydrogen, higher is the tendency to lose the electrons. So here comes the Nernst equation. If a metal ion after gaining the electrons converts into a solid metal, so Nernst has given an equation to find the electrode potential of the cell, EMF of the cell. E is equal to E naught minus 2.03 RT upon NF log concentration of metal solid upon concentration of its ion, where R is your gas constant, and here in electrochemistry we take the value of R as 8.314. F is your Faraday constant and it is your 96487 coulombs per mole. N is the number of electron transfer and T is the temperature in Kelvin. N positive is the concentration of the species Mn positive, and the concentration of the metal ion, which when it is in solid state, is taken as 1. And on solving these values, because 2.303 R, T and F are constant, only the value which are going to change is your N over here. All the values are common, and on solving these values, the value is your 0.0591. So the equation can be formed as E cell is equal to E naught cell minus 0.0591 upon N log the concentration of Mn positive. And if there is a galvanic cell, this is for the half cell, and if I use it for the your Daniell cell, it will form the E naught for the half cell and E naught for the second half cell, oxidation half and reduction half. And then we have to separate these two halves equations. E naught is your cathode minus anode, so it will be the cathode reaction minus the anode reaction, and at last we get that E cell is equal to E naught cell minus 0.0295 log RT upon your NF log to the power Z concentration of Zn2 positive ion oblique concentration of Cu2 positive ion, or in short term we can say E cell is equal to E naught cell minus 0.0591 upon N log the concentration of anode upon the concentration of cathode. So this is the your Daniell cells or the Nernst cell equation. Then there comes the equilibrium constant from the Nernst equation. If we find the equilibrium constant from the Nernst equation, it is your minus log Kc. Kc represents your equilibrium constant equal to N E naught cell upon 0.0591, where N is the number of electron transfer. There is another one, Gibbs energy, and it is your delta G naught equal to minus NF E naught cell. Now we will come for the conductivity of the cell. We know that resistance is the oppose of the current, and for this the Ohm's law has been given to us. The amount of current is proportional to the voltage applied to the circuit and inversely proportional to the resistance of the circuit. So According to the Ohm's law, the resistance is the property of the substance to oppose the current, and for this we have the specific resistance also. So particular material have a specific resistance, and it is denoted by your rho. We know that R is directly proportional to length and R is inversely proportional to area, and to remove this proportionality sign we are having a constant known as rho. So rho is equal to your R A upon L, where rho is your resistivity, right? R is your resistance and A is your area and L is your length. If area is 1 meter square and L is your 1 meter, so the resistivity becomes equal to resistance. Its unit is your ohms centimeter or ohms meter. Then there comes the conduction. Conduction is the ease with which the current flows through the conductor, and it is defined as the reciprocal of your resistance. So it is denoted by your G or capital C. Capital C is equal to 1 by R and its unit will be per ohm. There is another term comes conductivity. Conductivity is the reciprocal of resistivity and it is denoted by a symbol known as kappa. So it is defined as a conduction of 1 centimeter cube of the conductor. There is a relation between conductivity and cell constant. Kappa is the reciprocal of specific resistivity. So rho, we know that it is R into L upon A. So kappa is equal to 1 upon R into A. So kappa is equal to conductivity into L upon A. 1 upon R is your conductivity and L upon A is your cell constant. So conductivity is equal to conductance into cell constant. There is another term known as molar conductivity or molar conductance. The molar conductivity of an electrolyte solution is defined as its conductivity divided by its molar concentration. It may also be defined as the conducting power of all the ions produced by dissolving 1 mole of an electrolyte in a solution. Therefore, molar conductivity is specified as kappa upon C, where C is your concentration, molar concentration of the solution. So it can be defined as molar conductivity is equal to kappa into 1000 upon C. The unit of molar conductivity is Siemens meter square per mole or S meter square per mole. There is another term, electric equivalent conductance. It is the conductance of 1 gram equivalent of the electrolyte dissolved in volume cc of the solution. Equivalent conductance is represented by inverted V upon EV, and it is your kappa into volume. Here the volume is 1000 upon normality. So the concentration here will be normality. So specific conductance or conductivity is the conductance of 1 centimeter cube of the solution. Upon diluting the solution, the concentration of the ion per centimeter cube decreases and therefore the conductivity also decreases. But kappa, the molar conductivity, will increase because molar conductivity is the product of kappa into your volume, and during the process volume increases on dilution, therefore our molar conductivity also increases. From a graph, it has been noticed that the variation of molar conductivity with concentration is very small for the strong electrolyte, and if we plot extrapolation of the graph, then the zero concentration will be measured, and that concentration is known as limiting molar conductance or the infinite molar conductance. But for the weak electrolyte, as the molar conductivity is much lower as compared to that of the strong electrolyte, the variation is very large of the molar conductance, so that we cannot obtain molar conductance at infinite dilution by extrapolation. So for this we have a law known as called Roche law, and it's defined as at infinite dilution, when dissociation is complete, each ion makes a definite contribution toward the equivalent conductance of the electrolyte, irrespective of the nature of the ion with which it is associated, and the value of equivalent conductance at infinite dilution of any electrolyte is the sum of the contribution of its constituents ion. So here is the example of the molar conductance of the weak electrolyte. We have to find the molar conductance of the weak electrolyte acetic acid, and we have bifurcated it as CH3COO negative plus H positive as equation 1, and has been given as CH3COO Na, which has been again bifurcated as CH3COO Na plus Na positive. HCl has been bifurcated as H positive plus Cl negative. NaCl has been Cl negative Na positive. From the given data, we required the CH3COO Na and H positive. Therefore, we added these two terms and subtract the terms which are not required for us. For example, Na positive and Cl is not required. Therefore, this whole term is subtracted from it. So the application of the Colruy's law is that it is used for determining of the degree of dissociation of a weak electrolyte, which is molar conductance at a concentration to the molar conductance at infinite dilution is represent your degree of dissociation of the weak electrolyte. So it can also correlate the dissociation constant of a weak electrolyte as follows. So Ka is equal to C alpha square upon 1 minus alpha, and putting the values over here, we can find the value of acid constant. So by this, the chapter has been completed. Hope you all have understand it. We will do the numerical in our sessions.